Hello everyone. In this video we're going to take a short look at some of the tools that we at FixedIT have available to help you be more efficient while developing your own deep learning models for the access cameras. As we all know, creating a model for the DLPU in the access cameras is significantly more challenging than creating a deep learning model that will run on a host computer, because the DLPUs, the neural network accelerators in the cameras, are much more limited in the number of operations that they support, and sizes of tensors and combinations of all kind of different things in the model. So when doing that, it takes a lot of experimentation, a lot of testing back and forth on the device. And if you constantly do this in your Edge application, in your ACAP application, then it will be a very slow process of developing your model, since you constantly need to make changes in your C or C++ code and debug the model output from there. So what is our standard workflow when we are working with new models in the access cameras is that we make use of a context manager that we have created, which allows us to run Python scripts directly on our develop computer, and just with a single function call run those models on the camera. So to show you how this works, and this script that includes this context manager is part of our developer program helper scripts, meaning that everyone that has signed up for our ACAP Developer Acceleration Program will get access to these scripts and can make use of this for your own deep learning development. So to show what this script can help you with, I'm going to start with an interactive Python prompt. So again, I run this directly on my developed computer because I want fast iterations. It's here that where I have my images. It's here that I can visualize scripts with matplotlib or whatever I want to show. But I still need to run the model inference on my camera that is here behind me, because if I run it on host, then it will not behave the same as if I run it on the camera. That's the challenging here with the deep learning processing units, that we need to actually benchmark and test how and if it runs in the camera. So I'm going to start with importing a few different functions from this script. And the first thing we're going to do is to list what devices are available. So I'm going to create a connection to one of the cameras I have here behind me. I just need IP address and an SSH user for this device. And then I'm going to get available backends on this device. So now I know what backends is available, and the DLPU is the one that you most frequently want to use for deep learning projects. So let's try to run a model inference. The first thing we're going to do is to import NumPy to create some random data for the input. The second thing we will do is that we will create a context manager that gives us a connection to the camera where we can run model inferences. So let me just step through here. So this is what we want to do. In this case, we're using another camera device. It's the IP170. And again, username and password for an SSH user, and we're going to specify what accelerator to use. So this is what you copy paste from this output here. In this case, we ran it on an RPEC-9 camera here, so we got the RPEC-9 outputs. Now I have it on the RPEC-8 camera, but I could of course change that to run it on the RPEC-9 camera instead. And of course we also need a path to a model that we should run. So this is the TF-Lite model, a unit model that we have created for the RPEC-8 and RPEC-9 camera. So let's again try to run this context manager. So what we say now is, let's see, I thought we did run the random array, but apparently I didn't. So here we create a random data array that we use for input. You could of course also load your image and do whatever pre-processing you need to do, and you can do the pre-processing on the host device in this case. Now we should be able to run the model inference. So what we do here is that we create a context manager that connects to the camera, and it connects to the DLPU in the camera, and then we just call run inference function every time we want to run an inference. So you can of course keep the context manager open and do multiple of these function calls if you want to do more than one inference. So then we don't need to recreate the connection every time. So this is as easy as it is to run inference on a camera device directly from a host computer, instead of having to manually run a lot of different SSH commands or other kind of challenges. One of the really annoying thing lately has been with RPEC-9 chip that if you have a camera that is only available with Axis OS 12 plus, then the CLI for LARA does not work as intended using those users. But there is a workaround that you can do involving multiple different SSH users to run the command and get the files and so forth. But it is a big mess to do that manually. But with this context manager, it handles that also. So you can run this on your RPEC 8 or RPEC 9 device instead. If I do 166 here, we need to change to another SSH account that I have in this one. The accelerator should instead be RPEC 9 the RPEC 9 DLPU. And the thing that we need to do differently here when using the workaround for the current Axis OS 12 bug is that we need to give it another username and password to a user that we should use. And let's just go to the device quickly. So this is our RPEC 9 device, and it's this user here that we want to use. This is essentially just an SSH user created so that it has access to the large users, that it is a member of the large users group. And again, we need a password for this user too. And let's remove, so we just run the inference once. And here we have, again, the result from the RPEC 9 device. So this is how easy it is to run inference directly from your test scripts using the DLPU in your different computers, if you make use of this this camera inference helper script that we have available to all our members of the Axis Developer Acceleration Program. But we have more than that. We also have this compare inference script because, as I said before, you shouldn't expect the same results when you run your models on host as when you run them on the device. Even if you have done exactly the same quantization and run them in the DLPU in the camera, it will be different from if you run it on the CPU on your host. And it will actually also be different in a third way if you run it on the CPU in the camera. So that is something that has hit a lot of people in a bad way. Maybe they're not even realizing that, and that they are just experience worse performance on the device than they expect. So we have a script that also is included in this developer program helper scripts repository. So this script allows you to specify a deep learning model and image that you should run. And again, camera IP, username, password, the accelerator name, and for RPEC 9 cameras, this extra user to get around the bug. But let's see. we will again run this UNet model that we have created. We have an image here that I'm pointing at, and we run it on the ARPAC-8 camera, so we just need IP, username, and password, and the accelerator name. So let's start with running it on the CPU in the camera. So what this script does now is that it pre-processes your image, it runs it both on host and it runs it in the camera, and then it compares the differences so we can see how much does the output values differ. So this is typically what you will see if you use an operation, for example an activation function that is not supported well in the DLPU, is that you will see that you get massive differences between the host and the model. Or of course it might not even load on the device at all. In this case we can see that most of our values are 0, so no difference at all between host and target, but we have a few that are differs a bit, and we can also see some statistical metrics here per channel. In this case we just have 2 channels and a single tensor, so it's not super interesting or complex data in this case, but still helpful. But we can also run it on a more complex model. So in this case we run it on a YOLO model. We can run it on the ARPAC-9 this time, and let's see how this looks. So now it again runs it both on the CPU on my host and on the DLPU in the camera, this time the ARPAC-9 DLPU. And here we can see that this model has multiple channels in this tensor. And here we can see for each of the channels how the outputs differ. So here we can see that we have a very big difference between running it on host and running it in the camera. So this is something that can definitely affect inference quality a lot. And since you know which channel and which tensor it is, it helps you to find the operation that is actually causing this discrepancy. But it doesn't automatically isolate the specific operation. So you will still need to run this test multiple times. And what we tend to do is to create some automated script that is using the context manager directly to create the model in different variants, try to run them all, and then just create a big presentation of it all so that we can look at it and see what is actually causing these issues. And another thing you can do is that you can very easily create scripts for doing this. So if we take a look at this script that I have created, just a super simple script that will run our UNet model. So our UNet expects an input of shape 224 to 24, 3 channels, since it's RGB data, single batch size, and unsigned int 8 as input. And the output will be essentially the same, but just 2 channels. So in this case, we have 1 channel for background and we have 1 channel for white powder, which is what we want to detect with this particular model. I have created 2 different configurations here for the 2 cameras that I'm using, one ARPAC-8 camera and one ARPAC-9 camera. So I don't have to type this information all over every time I'm going to run it. I have a simple load and pre-process image function that will load an image from my host computer and pre-process it in the right way for this particular network and return the result. And a simple function to visualize the results in a plot using matplotlib. And then I have my entry point here with the different arguments. So here we are creating, this is the key here. We are using our context manager from the camera inference script to create this run inference function that will run inference on the device. And then we just call it here using the test input, and we get the outputs. And then we just use our visualization function here to visualize the results. So this means that I can now run Python test unit, and I'm going to specify the path to the model and the path to the image. And now I run this script. It will again connect to the camera, run inference. I can see here that the inference took 10.57 milliseconds. So I can already now get an indication of how fast it is running. But if benchmarking was what I wanted to do, I could, of course, create a script that will run multiple iterations of the model and create statistics over how long it takes, the average time, the minimum time, the maximum time, and so forth. And I could, of course, also create a script that trains different variants of the same model and compare them against each other, so that I can more or less automatically optimize the model for inference time. But what we see in the visualization in this case is our input image, which is a bucket with white powder, and we have our output image, the two-channel heat map, one for background and one for white powder. So we can see here that it pretty accurately segmented this powder. So I think that was all the things I wanted to show with these Python scripts here. There's so much you can do with these scripts to build your own advanced tools for customizing or for analyzing different models and helping you with the model creation and helping you with optimization of the models, helping you find supported operations, not supported operations, and so forth. So it's really a lifesaver for us when we're trying to get new models to run. Another tool that we have is for benchmarking purposes, to understand what is going on in your camera when you run your model. So this is typically not as much intended for the actual deep learning model inference in itself, but more the whole pipeline of running the inference over and over at high frame rate. Because we don't have any insight directly into the DLPU, but we can see the rest of the system, such as memory and CPU and so forth. And the CPU utilization is typically very useful to see when you're creating a real-time pipeline that is constantly running inference, because it might be that the CPU is bottlenecking the inference, not the DLPU, so then you can optimize for that. It might be that you're running a process single-threaded, so it's just one core that is fully saturated while the other ones is not. Then you would see in the graph here, if you select a smaller time span, you can see the different CPUs here. And if you see that when you start the application, one of the cores is going low, but not the other, then you know that you need to do more multi-threading or have some kind of event loop or something like that. We can also see, if we take a look back here on the last 12 hours, we can see that we have two big dips here. That has been when I have been loading new deep learning models into the camera. So whenever you load a deep learning model in the RPEC 8 or the RPEC 9 camera, this is an RPEC 9 camera, then you will trigger a just-in-time compilation of the model on the device, and that takes quite a long time. So we can see here around 10 this morning, I started one conversion. So let's select today's date, 20, 25, 11, 14, 10, 100 hours. And let's look at half an hour after that. So here we can see the model compilation. So we can see what happens to the free flash memory, we can see what happens to the free RAM, we can see what happens to the CPU and so forth. And we can of course also measure the duration of the compilation here. So we can see that it started at 10:03 and it was done at 10:10. So that is 7 minutes to do the compilation of this model. This was the UNet model. We can take a look on more recently here. We did another compilation which was a much simpler object detection model that we were running, and we can see that this started at 1849, it was done at 1851, so this is approximately 2 minutes duration for this compilation. So these are some of the things that you can measure with these dashboards, which are created by the FixedIT data agent. So all you need to do to get this information is that you need to get a license for our FixedIT data agent ACAP application. You install that in your camera and have it running while you run your other experiments, and that will give you all this detailed information pushed to a database that you can self-host. All the database components that you need are open source, the database and the dashboard. So it's InfluxDB that we're using, an open source database. It's Grafana, an open source graph visualization system. And these whole dashboards, this detailed camera dashboard, and many other dashboards is available on our GitHub as open source. So it's super fast to get this up and running, so you can start benchmarking your own cameras and see what is happening with your devices when you run deep learning, model inference, or other analytics applications on them. And it's of course both useful for developers to see what happens while they are developing to be able to optimize more, but it's also good to have this running in production system so that you can monitor the hardware that is actually running your model and make sure that everything looks good. So that this is some of the resources that we have available for deep learning development for the access network cameras. So if you're more interested in this, then just reach out to us at FixedIT Consulting, and we can schedule a meeting and discuss more how we can assist you in your development process.